So I'll be going over the problems for levels 3 and 4. So level 3. Let P of x and Q of x be two cubic polynomials such that P of 0 is equal to negative 24, Q of 0 is equal to 30, and P of Q of x equals Q of P of x for all real numbers x. And so you want to find the ordered pair P of 3 and Q of 6. So first we'll try to find what form that the polynomials P of x and Q of x are in. And so we let f of x equal ax cubed and g of x equal negative ax cubed. And so from here we have that f of g of x is equal to simply f of negative ax cubed, which is just negative a to the fourth x to the ninth. And at the same time, this is equal to negative a times ax cubed, and this is equal to g of ax cubed, or g of f of x. So f of g of x is equal to g of f of x. And so now we let a new function h of x be equal to x plus b. And so we then have that the inverse of h is just equal to x minus b. And so now we can look at the functions h of f of h negative 1 of x and oh sorry, h negative 1 of h. Excuse me for a second. Sorry. So h to the negative 1, h, the inverse of h of f of x, of h of x, and also we can look at the inverse of h of g of h of x. And so then we have that h negative 1 of f of h to the negative 1 of g of h of x, 1, 2, 3, 4, 5, 6, is simply equal to h to the negative 1 of f of g of h of x. And that's because h and h, the inverse of h, simply just cancel out. And now from here, we have that this is equal to h inverse of h of g of f of h of x. And now this comes from the fact that earlier we found that f of g of x is equal to g of f of x. And so now we can just see that this is equal to and so this is equal to h negative 1 of g of h inverse of f of h of x. 4, 5, 6. And now if we look at these two, we can see that this is now simply just the complete inverse. So basically this, if we let this be something like a of x and this be b of x, then this was a of b of x, and this is equal to b of a of x. And so these two are also inverses. And so what that means is that p of x and q of x are in of the form inverse of h of f of h of x, or inverse of h of g of h of x. Okay. And so now after this, we see that we are basically solving one inverse of h of f of h of x is equal to 24, and h inverse of g of h of, sorry, not x. In here it's now 0, no longer x. H inverse of g of h of 0 is equal to 30. And so the exact order doesn't quite matter because it's simply just f and h are simply just negatives of each other. And so, and when we plug this in, we just get that we are basically solving the equations a times 0 plus b cubed minus b is equal to negative 24. Oh, sorry, this is negative 24. And negative a of 0 plus b cubed minus b is equal to 30. And so if we add these two up, then what we get is negative 2b is equal to 6. So b is equal to negative 3. And when we take out this, when we substitute this value of b back into any of these, then we get that 27a plus 3 is equal to 30. I substitute it into this one. And so that means that a is equal to 1. And so what that means is that p of x is of the form x minus 3 cubed plus 3, and q of x is equal to negative x minus 3 cubed plus 3. And so that means that p of 3 is equal to 3 minus 3 cubed plus 3, or 3, and q of 6 is equal to negative 6 minus 3 cubed plus 3. And so this is negative 27 plus 3, or negative 24. And so what we wanted was the ordered pair p of x, p of 3, q of 6. And so that means that the answer that we want is just 3 comma negative 24. So does anyone have any questions? And if not, then let's move on to the next question. Okay. Level 4. So find all functions f from the integers to the integers such that f of x plus f of t equals f of y plus f of z for all rational numbers x less than y less than z less than t that are in an arithmetic progression. Okay, so first of all, to solve this, let's define a new variable x and a new variable a that are both rationals. And so if we substitute, so we can substitute the x with x minus a, and t with x plus 0.5a, and z can be substituted with x, and y can be substituted with x minus 0.5a. And so that just gives f of x minus a plus f of x plus 0.5a equals f of x plus f of x minus 0.5a. Okay. And so next we can make a similar substitution, except this time we let x be substituted with x minus 0.5a, t goes to x plus a, c goes to x plus 0.5a, and y can be substituted with x. And so the resulting equation from this is just that f of x plus a plus f of x minus 0.5a is equal to f of x plus 0.5a plus f of x. And so after this, we can see that we can just let f of x plus a minus f of x. And so from this equation, we can see that it's equal to f of x plus 0.5a minus f of x minus 0.5a. And from the first equation, we have that this is equal to, so this gets subtracted to there, and so that would get subtracted over there. And so this is just equal to f of x minus f of x minus a. And so if we combine like terms, what we get is 2f of x is equal to f of x minus a plus f of x plus a. Okay, x plus a. Yeah. And so now we can, if we let f of 0 equal to k, then we can define g of x to be equal to f of x minus k. And so that would mean that g of 0 is equal to f of 0 minus k, which is k minus k, or 0. And so what that means is that 2g of x is equal to g of x minus a plus g of x plus a. And so if a is equal to x, then what we get is that 2g of x is equal to g of 0 plus g of 2x. And so we already saw that g of 0 is simply 0, so g of 2x is equal to 2g of x. And of course, we also have that g of x is equal to g of x. And so now we can induct. And so the goal here is to show that g of cx. And so first of all, so now we want to induct and show that g of nx equals ng of x for all integers n. And so the base case is simply the one already shown for the 2 case, or the 1 case. It could also count. So then now the next case is to assume that g of c of x is equal to c g of x for c between 1 and n. So then what we want to show is that g of n plus 1 x is equal to n plus 1 times g of x. So what we can do here is just substitute. What we do here is just substitute nx into where the x is and substitute x into where the a is. And so what that gives is 2g of nx is simply equal to g of nx minus x plus g of nx plus x. And so that by the inductive hypothesis up here, this is 2n g of x, and this is n minus 1 g of x. And so that means that g of n plus 1 x is equal to 2n minus 1 g of x, or n plus 1 g of x. And so what that means is that g of nx equals n g of x for all integer n and rational x. And so what that means is that as long as m is not equal to 0, then we have that g of x is equal to 1 over m, or just 1 over n, g of nx, or what that also could be is 1 over n g of x is equal to g of 1 over n times x. And so what that means, what that would imply is that g of n over m, so what that would imply is that g of n over m is equal to n times g of 1 over m. And so this is equal to n times 1 over m of g of 1, or n over m g of 1. And now, if we let g of 1 to be equal to m, then what we'll get is that g of x is equal to mx. And since we defined f of x to be equal to g of x plus k, then we have that, sorry about that, g of x plus k. So this is equal to mx plus k. And so what that means is that this is all possible f, such that all of the conditions are satisfied. So